Okay. I welcome you once again for today's third session of this 5 days faculty development program on advances in earthquake safe design and construction practice under AICTE training and learning academy. Our next esteemed speaker is Dr. S.T. Bharti. Sir is currently a professor of structural engineering in the Department of Civil Engineering and head of a National Center for Disaster Mitigation and Management in Malawiya NIT Jaipur. Sir has completed his bachelor's in civil engineering from MBM Engineering College, Jodhpur. Sir has completed his MTech in structural engineering and PhD in earthquake engineering from MNIT, Jaipur. Sir has more than 2.5 decades of teaching experience and has taught various disciplines of civil, structural, and earthquake engineering. Sir has supervised 10 PhD and more than 50 PG dissertations in the area of structural dynamics. Sir has published more than 25 research papers in international reference journals and in more than 100 international conferences in the field of structural dynamics and earthquake engineering. Sir is also a member of the Bureau of Indian Standards Committees for drafting of earthquake engineering standards and also the convener of the Committee for drafting of the Indian Standard for Base Isolated Buildings. It gives me immense pleasure to invite our next speaker, Dr. S.T. Bharti, sir. Sir will take this session based on use of earthquake energy dissipation devices in buildings. It is a privilege for our department to welcome and introduce Dr. S.T. Bharti, sir. One thing I would like to tell personally about sir, that sir has attended each and every session till now. Now I would like to invite Dr. S.T. Bharti, sir, to share his words of wisdom and a wonderful experience with us. Over to you, sir.
Thank you, Ms. Sheikh, and thank you very much. Am I allowed to share? Shall I share my screen and then? Okay.
Yeah, sure, yes, sir.
Is it? Oh, just a minute. Share screen. And is the presentation visible to all of you?
Yes, sir.
Yes, sir.
Are you able to see my screen?
Yes, sir.
Yeah, yes, the screen is visible to all of you. Yes, can you see the screen, please?
Yes, it's visible.
Okay. So good afternoon, everyone. I'm going to talk on seismic design and supplemental energy dissipation devices. So this is going to be a new kind of thing. So this is the discussion for today. First, I'll talk about some basics about seismic design. We have been talking about seismic design in all these sessions, but since just to maintain a continuity of the talk, I'll give you some background about seismic design in general, and then why do we require supplementary energy dissipation devices? Of course, this is an application in seismic engineering or seismic design only, and then seismic energy, a new concept, because so far we have been talking about force and displacement. Okay. And then influence of damping or energy dissipation, modeling and analysis of supplemental energy dissipation devices, or what we call shortly called SEDs, and then application and caution. These are going to be the broad line of our discussion for today. So this is the first. Let's go the background. The picture you can see in background, we'll talk about that later. See, your college name is LD. Can you hear me? So there is a LD3 of seismic behavior. I can see the echo of the sound. Can all of you mute your mics? Yes. So this is the LD of seismic behavior. The first thing is the load path and flow forces. The load path from the source to destination, how the load travels. That is what you have to understand very clearly as a student as well as a designer. So this is the first L of LD, load path and flow forces. The D is dynamic character. There are The first one is the dynamic characteristic of the structure. That is the D of the LD. And when you talk of dynamic characteristic of the structure, the most important is the natural period. There is a S in the parenthesis, meaning thereby most structures will have more than one natural period. The longest or the most flexible and most energy taking we call fundamental. And generally most of the designs are based on only few modes. Okay. So the first dynamic characteristic is the natural period. Second dynamic characteristic is the modes of oscillation. Okay. So please understand these two are the intrinsic structural dynamic characteristic. They have nothing to do with the loads. Okay. Regardless to the load, these are the dynamic characteristic or these are the characteristics like material property. These are structural properties which will exhibit or which will show their impact on structural behavior under dynamic excitation, be it earthquake, be it any other dynamic excitation. And when you talk of modes of oscillation, other speakers have been talking about no torsion mode of oscillation. I'll tell you why torsion is such a big no. Those they understand basic soil mechanics will appreciate that torsion is actually shear stress. Okay, and shear stress, in shear stress, the strength of the material is quite low and it is very quick also. So that is the reason typically the concrete shear strength is even less than 10% of its compressive strength or normal stress, and its failure is also quick. So that is why we all the time say no torsion. Then the third dynamic characteristic is of course damping. Typically we assume, and damping is actually what we assume 5% in Indian standard, other standards. This is the material property. Previously, in the previous standard, there used to be 2% and 5%. 2% for steel and 5% for concrete. Now we have 5% for both. Okay. So these are the dynamic characteristics. This is the D of LD. And then another D, you can see LD3 here. Another D is dynamic characteristic of ground motion, which is represented by three parameters: amplitude, which can be P ground displacement, P ground velocity or pseudo velocity, P ground acceleration or pseudo acceleration. And the next one is the frequency content. The third one is the duration. Here I want to underline is that the duration effect, the analysis process that we are doing using are the static methods are not accounting for duration effect. The next D of LD is damage distribution. How, as you have been listening from other speakers, that under design earthquake, building is bound to undergo in the inelastic range. It cannot remain in the elastic range under the design load. So there is bound to be some damage. Damage, inelasticity, non-linearity. These are the three words which are interchangeably used, but you have to understand. Damage is the manifestation of inelasticity, and non-linearity is the cause-effect relationship of force deformation when a building gets in the inelastic range. So non-linear behavior, non-linear analysis, inelastic behavior, and damage. These are the three terms which are interchangeably used, but the focus of each one of them are different. So damage, how do you want damage? You want damage at a desired location. Having understood that under the design earthquake, your structure is bound to get into inelastic behavioral range. That means damage is bound to happen, but you do not want that damage is such that the damage in the base of the column and structural collapses. You don't want that. You want to dissipate energy through desirable mode of damage. So what is desirable? Location and nature. And the most desirable location is beam ends, and in the beam ends also you do not want brittle, you want ductile. So ductile means you want flexural basically, no shear and no torsion. Okay, so this is the LD of seismic behavior. These are the three things you must understand. One is the load path, second is the dynamic characteristic of the structure, and then second, you can say second A, you can call it second B, so that you become LD, so that it's easy for you to remember. The second D is the dynamic characteristic of the ground motion, and third D is the damage distribution. So this is the LD of seismic behavior. If you understand these three things, you will appreciate that all through the lectures and all the lectures, these three, if you remember these LD, all is done. Next. And in the previous slide, we saw modes of oscillation is the biggest problem for us. I mean, if you are able to control the modes of oscillation and you are making sure that the torsion and other quick modes or brittle modes are avoided, then half of your job is done. Now let's understand how modes of oscillation are controlled. The biggest thing or the simplest thing and the most dominant thing to control the modes of oscillation is configuration. And the IS 1893 describes the configuration by way of this is not, this is not, this is not. I mean, if this is then it's irregularity. So configuration is actually defined negatively by way of defining irregularity. So irregularity are essentially of two kinds, plan irregularity and elevation irregularity. Plan irregularity can be re-entrant corner or you can have a non-parallel lateral. Please understand this is in plan. And this is an elevation. So if you have a non-parallel system, and there are things in both plan and elevation, they are quite similar. Re-entrant corner in plan and re-entrant corner in the vertical also. In vertical, when you have a re-entrant corner, you call them box columns, or what do you call them? Discontinuous columns. Like if you have a structure like this and there is a column coming and then suddenly it just goes in and then there is a column. So this is kind of re-entrant in vertical offset. And you have a non-parallel lateral load system, and then lateral system discontinuity can be horizontal, it can be in the vertical also. Then diaphragm discontinuity, and then you have a weak or soft story. Weak means it doesn't have the sufficient strength. Soft means it doesn't have the sufficient stiffness. Let's understand. See, this is your soft. And this is your weak. Both of them having same strength practically. Okay, so let's move on. And let's understand attributes of a good configuration. What your configuration should have in order to have desirable modes of oscillation. It should have low width to depth ratio, so there is no torsional effect. It should have low height to base ratio. We call them slenderness ratio and aspect ratio. So there is no low overturning moment. Similar story heights, dissimilar story heights will create stiffness irregularity if you are to use 1893 language. Short span, low unit stress and symmetrical plan again will have a good deformation behavior. Uniform, again it's a stiffness. So these are the things, they have been worded differently. If you missed one, what is the consequence of redundancy? Means alternate load path. Okay. In earthquake, since we are allowing damage, you always want redundancy. Please understand, redundancy may be a problem for your analysis. But for structure under earthquake, redundancy means if one member yields or one member gives way or one member gets into the plastic deformation, there is an alternate load path. Okay, let's move on. So see, earthquake design is about matching capacity with demand. So this is the terminology which most undergraduate classes we don't learn. But in graduate classes and doctoral programs or in the typical literature of earthquake engineering, you will find capacity and demand. Originally, these are the terms which have actually come from economics and management. But civil engineering or structural engineering, particularly in the West, is quite influenced by the economics. So that is why these terms are. So let's understand what are the demands and capacity in terms of earthquake engineering. And these are the two things in that the word demand is used. Loading imposed is also known as action part, which is also called earthquake demand, which leads to force loading as well as displacement. Please understand, I am not saying that in the linear elastic range, force and displacement are quite okay. But in earthquake analysis case, it's a displacement loading which is critical, which is the load actually. What you are doing in earthquake is that you are shaking the ground, you are trying to displace the ground. And because you are trying to displace the ground, there is a mass sitting on top of it. The mass will experience inertia force, inertia effect, and then inertia effect will generate inertia forces which will be getting transferred from top to bottom. So that is why, and what is causing is displacement. In other loads, see, force and displacement will always happen together. In normal gravity load, there is a force, or there is a load, there is a force loading which will create deformation. In earthquake behavior, there is a displacement below the ground which trying to move the building base or the whole of the building. Since there is a mass, it is offering resistance or inertia effect. So this is the loading imposed load action part. Loading imposed is the action part of the demand, and the consequences part. Consequences part is response, which is called engineering demand. Please understand these two terms very clearly, because these are the terms. This is engineering demand and this is the demand in terms of loading. For both the things, the word demand is used. Engineering demand means because of the loads, because of the earthquake excitation, your structure will experience axial force, bending moment, shear force, torsion, and reduce to the material level stress and strain. So both are demand parameters. This is the loading demand, this is the engineering demand. Now capacity is the maximum capacity or maximum availability. Please understand, this is availability. And this is defined by in terms of limiting value of stresses and strain. And this is defined also in terms of force capacity and also in terms of deformation capacity. This is more relevant when we do capacity design. We are not talking here capacity design, but you must understand in earthquake design, you have to understand both the force capacity and deformation capacity. This is the main, deformation capacity is the main element, but certain elements are designed for force capacity also, particularly when you are using capacity design, because all the elements cannot be designed for deformation capacity. Let's move on. This is a very good chart. In that we are talking about seismic demand, design philosophy, performance objective, and the limiting engineering parameter. The first one is the seismic demand or hazard level. As you know, the earthquake has to be defined in terms of its probability of happening or probability of accidents. We are assuming, what is assumed is that Poisson's distribution. And design life is 50 years, which is generally design life for most buildings or regular structures. So if you have a service level earthquake, which is a minor earthquake and which is actually a frequent happening, so it will have 50% probability of happening in 50 years of design life. So using Poisson's distribution, it gives you 72 years of design life. And what is the design philosophy for the service level earthquake? You do not want any structure, but no structural damage, or some people say minor non-structural damage. Okay, because nowadays the design objective is defined both in terms of structural damage or non-structural damage. So you can say no structural damage, or you can say no non-structural damage also. No NSD also. And what is the performance objective? Because performance-based design or performance evaluation has become a buzzword now. You will learn about that more when Professor Murthy talks tomorrow. What you want is the continued operation or immediate occupancy. These are the two terms interchangeably used. Continued operation means you don't have to leave your building premises and you continue to operate. Immediate occupancy is slightly more, because where it just began to at the touch of the yield. Okay, and the limiting parameter is the serviceability, and this is controlled by initial stiffness. Please understand that Indian standard provides some limiting value of say 0.4% drift, elastic drift, to meet this requirement. 1893. Now next level is the design basis earthquake, which is a moderate earthquake which happens occasionally. It has got a 10% return, 10% probability of exceeding or happening in 50-year design life, which will have the return period of 475 years. These two calculations are interlinked, and this is based on Poisson's distribution, which the formulae for calculating from, see, if you use design life, probability of exceeding, and return period, all three parameters are connected based on probability distribution assumed. And what you want is that you want repairable structural damage here, and this is called damage control or life safety performance objective. Okay, and this is governed by strength, how much maximum it can take. And the last one is the maximum considered earthquake or severe earthquake, or it's a rare event. It has a probability of 2% in the design period or design life of 50 years. It will have a return period of 2475 years. And what you are looking for is that the building should not collapse if a 2% probability earthquake happens. And performance, I mean, these we have been doing. Now the new word is a collapse prevention performance objective. What is your limit state is a survivability and ductility. These are the things which will help you in there. So the next thing is that, just a minute. Yeah, there is something. Yes, is investigating seismic behavior. Just remove this. This is not there. This is from the next slide. Okay, so now what are the methods of investigating seismic behavior? If you want to if your interest is only up to elastic behavior, you don't want to get into the inelastic range, which is our code as of now, which tells you that you investigate up to elastic behavior, follow certain prescriptions, and you kind of assume that in case of the design earthquake, in case of severe earthquake, your structure will follow the well-defined deformation or ductile deformation path. But your actual investigation is limited to only linear elastic limit. So there are two methods like linear static methods, in that the input is taken from design spectra or response spectra or any kind of spectra, which can be, there are variety of spectra, and both the methods are actually static methods. Equivalent static method or equivalent static single mode method, in that our code calls it equivalent static method. The code tells it equivalent static method, ESM. The other one is also equivalent static, but we are using is multi-mode, which is called response spectrum method. The code call it RSM. Plus, but you will understand that in both the methods we are applying, in order to take the inertia effect into consideration, we are actually applying static loads. We are not considering the dynamic. We are considering dynamics of the structure by way of choosing the acceleration, but still we are applying the static load. Okay, and in the acceleration itself we are accounting for the damping part, but still I would call them application of equivalent static load. And equivalence is based on the maximum value of acceleration and then damping in the structure. The first one is when you are assuming only single mode. The next one is when you are assuming, when you are taking all the mode and then you are superimposing them. And then this is the dynamic method, linear dynamic method. Using in this input require is the ground motion. You require ground motion history. There are two ways of doing it. One is the response history method, other one is the modal response history method. Please understand the modal response history or modal response spectrum method, both are kind of superposition. One is in the frequency domain, or each mode separately calculated and then put them together. And the first one is the time stepping integration scheme. The next we move on to, this is actually the nonlinear method. And then the nonlinear method also, there are two methods. One is all nonlinear methods are basically on pushover. And pushover methods essentially depend on two things. One is that what is the distribution of the distribution of the lateral load or lateral push. Your objective to apply lateral load, that you want to imitate the inertia effect. You may have lateral load which is distributed like this, You may have a lateral load which is uniformly distributed. Depending upon how your superstructure is behaving. Okay, so depending upon that, the nonlinear static method, or what is popularly known as pushover based methods, are two: conventional pushover and adaptive pushover. In conventional pushover based methods, once you decide the pattern of push based on initial stiffness or initial mass or initial damping on fundamental mode, you fix the push pattern and you continue with that till the time your desired point or point of interest is reached. In adaptive pushover, every push you update the K and M, and once the K is changed, you keep changing the push pattern. So this is how the nonlinear static methods are of two kinds. One is the conventional push and other one is the adaptive push. In that you keep on updating your model. You means the computer keep on updating that model. And the push and another parameter that you need to define in pushover analysis is the modeling of component inelastic force deformation behavior and what is known as backbone curve. These are the two things. So this is the nonlinear static method. The second one is the nonlinear dynamic method, which is also known as nonlinear response history method. In this also you require force deformation behavior under reverse cyclic loading. In this you require complete hysteretic behavior or cyclic behavior of the component. So these are the methods of analysis. So these are some of the component force deformation behavior. We always love this because this is the one which dissipates maximum energy. It goes like this, and then when it comes back, it takes full shape. There is no deterioration. Whereas in this case, once it comes back, while the returning phase, there is a degradation in the stiffness. And every successive cycle, the first one is the outer one. And every successive cycle, it comes back in. So there is every successive cycle, the energy dissipated is reduced and the stiffness is getting declined. Pinched are typically when you have some slip or some kind of mechanism in that every time there is a slip. So this is the pinch hysteresis loop. There are some cyclic degradation. Every cycle there is a degradation in stiffness and strength. So these are some of the idealized typical hysteretic behaviors that you would require to plug in when you do your actual nonlinear response history analysis, or you can call full dynamic analysis under nonlinear conditions. And this is the philosophy as we had discussed the table. In the minor shaking, there should be only minor non-structural damage, but no structural damage. In the moderate, you have some damage in the structure, and in the strong, you have significant structural damage, but no collapse. This is the design philosophy we have been familiar with. These are the 7 attributes. First one is the configuration. If your configuration is good, there is no stiffness and mass irregularity both in plan and elevation. Your structure modes of oscillation will be perfect. There will be no stress concentration. Even though there is a damage, the damage will be well distributed and there will be no quick, brittle or sudden collapse or failure. The second one is the stiffness, which actually governs your serviceability. Initial stiffness you want good enough so that under the minor shaking condition, the non-structural elements are secured. The third one is the strength. The fourth is the displacement ductility or system ductility. Fifth one is the total, how much it can deform as a system so that energy dissipation is maximum. And all you can do when you choose a desirable collapse mechanism. You are all familiar with these 7 attributes of seismic design. Based on these, there are 4 methods of seismic design. One is the stiffness, other one is the strength. These 2 are currently in use. Deformation based design is in practice. As you know, deformation based design essentially relies on nonlinear analysis. Our energy based design is still in the developmental stage, which will combine both force and deformation together in a nonlinear range, which is very difficult as with the kind of knowledge, because what you require in deformation based in energy based design is the nonlinear component force deformation behavior. Okay. So with that, the background part is over. Now let's move on to supplemental energy dissipation devices. What do the supplemental energy dissipation devices do? Just wait a minute. What you can see in the background is the newly set up National Earthquake Test Facility at MNT Jaipur. We'll talk about that on subsequent slides if the time permits. Okay. Why do you want to have supplemental energy dissipation device? The basic purpose is performance enhancement. Okay. How do you enhance the performance? As you have seen that your structure undergoes damage. And why it undergoes damage? Because earthquake pumps in the energy and that energy has to be dissipated without much of the damage. So if you can create some mechanism by which energy can be dissipated by some desirable structural components or structural element which can dissipate energy without endangering your main structural system. So that is what the performance enhancement is. There's no structural damage, there is no non-structural damage. So that's called the purpose of supplemental energy dissipation device is energy dissipation, which is actually called as damping. Literally, damping means lowering of the response amplitude. But why that happens? That happens because energy being is sucked in. And when you do energy dissipation device or when you install energy dissipation device, it will also increase stiffness and strength, or it may typically. The terminology used are supplementary energy dissipation devices or damping devices or protective devices or a structural control. Please understand these four are similar but not same. Supplemental energy dissipation devices, I would prefer the term supplemental energy dissipation device. Why supplemental? Because this kind of supports the energy dissipation capacity of your primary structure. And how do they do? They will have damping. But when you say damp, this is the primary purpose. They create an additional energy dissipation capacity to save the main structural system. So this, I would prefer the term supplement energy dissipation devices. But if you say damping device, means you are actually discounting that the device will have damping only, but it will have stiffness also. So this is a half definition, or it does not, communicate the full meaning of the system or the structural component in place. Protective device is again is a market oriented term because it protects your the main structural system or seismic force assisting system. So you call it protective device. And a structural control system is again happening research term because you are able to control the response of the structure. That is why you call a structure control device. So looking at all the three: supplemental energy dissipation device, damping device, protective device, structural control system, I would go with supplemental energy dissipation device. But each of the term will have a different focus and different message to communicate. Structural control systems are typically classified into three forms: passive, active, and semi-active. Passive means no energy is required, and with the motion of the structure, you are placing them in such manner like in bracing and the bases so that it dissipate the energy and it kind of absorb the energy and it kind of saves the main structure or main structural frame system from damage. Active means you will have to apply an active force so that it kind of takes away the impact of the earthquake. Semi-active is actually passive in the sense it does not require any energy, but you can kind of control them by applying certain or few voltage of it. Active devices are like you are applying a counter force to the, if the building is going in left, you are applying a counter force from the opposite direction. So active are more or less not so much in application. Passive and semi-active. Semi-active is an extension of passive. In the passive device, there is a stiffness, there is a damping, and there are all arrangements. So by some way, if you can kind of change the passive, the damping or stiffness of a passive device, it becomes semi-active. Some people call it controllable passive also. So this is let's understand the terminology of supplemental energy dissipation. This is all about it. And supplementary energy dissipation devices are essentially of two kinds. Let's understand supplemental energy. I would be using the word supplemental energy dissipation devices consistently, not damping device, not control system, not protective system. Okay, because this is a term which says it all. So supplemental energy dissipation devices are actually structural elements. Please understand that. Let's demystify this. They are no magic wands. They are just structural elements. And what is the specialty about this structural element? This is structural element is the one which is factory made, which is designed such that you know the force deformation behavior of it to the best possible. They are factory made products and they are to be fixed appropriately to some structural location such that they perform the desired function. They are just like any other structural element, but with the difference that you know the force deformation behavior of it. And in the nonlinear range, since they have a big fat force deformation loop, they are able to dissipate substantial part of energy. And some people can ask various questions, which we will take later. That dissipate energy due to all structural elements will undergo deformation because of the relative motion. So are the structural elements. So because of the relative motion of each end of the device, they will dissipate energy. They will dissipate energy because they are inherently inelastic in nature. And under cyclic loading, they do not follow the same path. Okay, so that is why they dissipate energy, as we have seen various hysteresis loops. So supplemental energy dissipation devices, also known as damping devices, the terminology you are already understood, may be classified as either displacement dependent or velocity dependent. Displacement dependent, we call them. Displacement dependent means at a particular point or a particular instant of time, the response is a function of maximum displacement. The fourth response is a function of maximum displacement. Okay, you can call them rate independent also. The other class is the velocity dependent. In that, the force is a function of instantaneous velocity. The fourth response is a function of instantaneous. Simply understand these two are the pure category, displacement dependent and velocity dependent. Displacement dependent also called as rate independent. Velocity dependent also called as rate dependent. That means they are not only dependent on displacement, they are dependent on rate of displacement, which is velocity. Okay. Or you can have a device which is a combination of this. All the devices, the behavior of those devices, as I told you previously, supplemental energy dissipation devices are essentially structural elements. They are factory made, configured, designed, controlled in such manner that their force deformation behavior is known to you well in advance in the entire range of nonlinear, cyclic, reverse cyclic loading range. So their behavior can be nonlinear or linear also, depending upon the device and situation. The fourth response primarily is a function of relative displacement between when you have a displacement dependent device, you have their force is relative displacement dependent and is substantially, please understand, substantially not so independent of relative velocity, or they are called them rate independent, and they exhibit hysteresis. Hysteresis means energy dissipation. See, exact word meaning of hysteresis is that the value of force at a particular time is not only dependent on the displacement at that particular time, but also depends on the history of loading. That is where you call hysteresis. But when you have the inelastic behavior in most metals will exhibit hysteresis. That means what has gone into the past will have a bearing on the present. You can say that way literally. So the hysteresis can be rigid plastic, which is in most cases friction devices. It can be bilinear. It can be trilinear. So displacement dependent devices are rate independent. Their behavior is, or the force at a relevant time will be mainly dependent on displacement value at that particular time. You can call them rate independent. Most metallic yield damper or friction devices are rate independent. But they are hysteretic. That means the force value at a particular point is a function of how much is the displacement value at that particular time, not how at what rate the displacement is changing in the next instant, but it is still dependent on what has gone into the past at the previous step. Okay, I mean, most of the human memory is actually hysteretic. We remember what has gone into the past, and our behavior at a particular time will be influenced by what has happened an instant before or a month before, for that matter. Now the next one is the rate dependent devices. Like the displacement dependent devices are friction devices or metallic yield devices. The velocity dependent or rate dependent devices are of three kinds, essentially solid, visco. Please understand, whenever you say visco means it is dependent on velocity. When you say velocity, that means they are dependent on rate of loading. They are dependent of rate of displacement. That is why this V and velocity dependent you can always remember. So it can be solid viscous, it can be fluid viscous, fluid viscoelastic, or it can be fluid viscous. Depend on rate of displacement of, since they are dependent on rate of displacement, you can call them frequency dependent. It means same, whether you call velocity dependent, rate dependent, or frequency dependent. They are just three words. That's all. It means same thing. When you say whenever you say visco means there is some kind of fluidity in the material which is undergoing deformation, which is bound to be affected by not only the displacement, it is dependent on the rate of displacement, how the next increment is going to happen. So these are the category of devices, metallic yield dampers. As you know by this time, these two are displacement dependent devices. These two are velocity dependent devices. You can call them displacement dependent. You can call them velocity dependent. You can call them rate independent. You can call them rate dependent. You can call it frequency independent. You can call it frequency dependent. Same thing. Then the last category is dynamic vibration absorbers. They are quite, in terms of function, they are different from these two categories. I'll tell you how they are different. The broader category is dynamic vibration absorber. There are two kinds, tune mass damper and tune liquid damper. The biggest difference between first, if I call this as category A, I'll call this as category B. So category A is the one where you place these supplemental energy dissipation devices. These category A is you place them in the load path from the inertia force where it is generated. I mean, typically in the bracings. It will be placed like this. But dynamic vibration absorbers are not placed in the load path. They are typically placed at the top of the structure. We'll discuss them when we move on. So let's talk about, this is the inside view of our lab, which is yet to be commissioned. What you can see on the left hand side is the biggest base isolation test rig, which is ready for commissioning. And this is the wall. This thickness of this wall with M55 grade concrete is 2 meters, and that other wall is 3 meters. And the height of it is 11 meters. And these are the holding holes, which has a capacity of moment capacity of some 5.5 meganewton per meter of wall engagement. And it has got a floor which has got similar holes. We'll see about whenever there is an opportunity. This is just by the way. Now let's understand energy, our input energy. See, earthquake pumps energy into the structure. From this slide onwards, we are actually talking about earthquake as an energy input mechanism. Earthquake pumps energy into the structure. Part of it is recoverable, part of it is irrecoverable. The recoverable is elastic strain energy or potential energy and kinetic energy. So if there is no irrecoverable energy, there will be exchange of energy between these two. And in that case, your structure will keep on vibrating from this end to this end, back and forth. But between these back and forth motion, every instant of time, there is a withdrawal of energy. There is a damping. And the most obvious, when the structure is only in the elastic range, is structural damping, and what should be called as inherent structural damping. That means inherent structural damping, because everything is structural. So I would prefer call it inherent structural damping. That is part of the structure by virtue of being a material. So this is called structural damping. As I told you previously also, the typical value of concrete and steel as IS code prescribed is 5% inherent structural damping, what we'll call Xi or damping ratio, 5%. So this is obviously there regardless to the fact whether the structure getting into the inelastic range of behavior or not. So that is there. So even if it is an elastic behavior, the energy is so less that the inherent structural damping is good enough to reduce the energy level. The structure basically after some few cycles get quietened and gets into the normal stationary or steady mode. But the energy pumped in is so much that the structure inherent damping is inadequate, then there will be some damage. This is called plastic energy. This is called inelastic energy, plastic energy, or damage. And the irrecoverable part is something, these are the three irrecoverable parts, 1, 2, and 3. This is good enough when your structure's input energy is quite less, earthquake is only minor or not very severe, then your structural damping is good enough. But if your earthquake is slightly bigger or severe earthquake, you need to have, the structure will get into inelastic. So there will be some damage. But if you do not want any damage, then you have to put supplemental energy dissipation devices such that the structure largely remain undamaged. You understand? The same thing has been put into the mathematical algebraic expression, recoverable part, irrecoverable part. The recoverable part is potential and kinetic. And this is the inherent structural damping. This is the inelastic behavior. This is the supplemental. So if you want that there is no damage, you increase this so that this gets down. No damage. This is how the energy balance is. Now let's understand that. This is the acceleration and the energy is pumped into the structure. This is the kinetic energy against structural energy. This is the inherent damping. This is the damage. And if you want that there is no damage, then you have to do this in order to, this is anyway there. Structural damping is anyway there. And if the energy is so much so that you don't want this damage part, you have to increase that completely. This is another presentation of graphical presentation of energy balance. Why do you require supplemental energy dissipation devices? Let's move on. Minor shaking, some cracks, moderate shaking, some non-structural as well as structural, and this thing. And if you don't want no cracks, no damage, no damage, no damage, then you have to put, just a minute. No damage, then you have to put some devices here. Sorry, here, somewhere here. Let's say windows are not there, then you have to put some damping devices here. Okay, so this is what the performance enhancement using supplemental energy dissipation device means. Okay, and this is the picture of Nepal earthquake. When you have a devastating earthquake like that, this is what's going to happen. This is what it's going to happen. This is the King Birendra University. These are some of the schools there. We had visited there. And this is the Nepal earthquake, what's called Origin Tower. What you can see here is that large number of cracks in the infill walls. This is how the energy is being dissipated. When the earthquake energy is pumped in, either you have to have devices, or if you can afford damage, but the question is, where do you not want damage? Here. This is the hospital building, where it is in the Nepal only. This is the hospital building, not to say that this hospital had supplemental energy dissipation devices, but this was the one hospital we observed there was absolutely no damage. So when you have a situation where you cannot afford damage under a severe earthquake, you have to have the supplemental energy dissipation devices. Now the question is, how does the supplemental energy dissipation devices influence the structural behavior? Let's understand that by way of some fundamental structural dynamics. This is the when you are increasing damping in the system, this is the actual response curve, that with damping your amplitude is reducing. 20% damping is quite less. So this is the response history. Now let's move on to acceleration response. When damping is increased, your peak ground acceleration is increased. Pseudo acceleration is actually coming down. Similarly, your displacement is also coming down. So this is the way of representing added damping. Here the influence is damping only. Okay. Please understand, supplemental energy dissipation devices will have damping as well as some bit of stiffness generally. Okay. So this is how you look at it when you look at the response history. This is how you look at it when you look into frequency domain, pseudo spectral acceleration versus period. Here the spectral displacement versus period. So up to certain limit, it is able to reduce both displacement as well as acceleration. Now let's understand that. This is how this is the viscous damper, this is the viscoelastic damper, this is the hysteretic damper, this is the friction damper, and this is how you have to place them. And what is happening because of this? The inertia force, it will have damping, it will have some stiffness. Therefore, the response is being controlled. What you can say, special structural elements, as we call that, they are special structural elements which will add damping and which will add some stiffness. So the third category, the first two category we have already seen, the viscous damper, viscoelastic damper, hysteretic damper, and these two, as you see, these two are basically displacement dependent and these two are velocity dependent. These two are velocity dependent and this is displacement dependent, as you can see. This is not to say that in the same structure you will asymmetrically place all. This is just to show that how they are placed. Okay. We'll discuss the placement of dampers in the subsequent slides. And this is your dynamic vibration absorber. Please understand that the dynamic vibration absorbers are typically placed on the top of the building, and the mass is 2 to 3% of the main structure. This is your main structure. And this is your supplemental or dynamic mass. It will have some K. And this will also have some K. And the ratio of M and K are so chosen that both of them have a same natural period, particularly a fundamental mode. So what will happen is when this structure shakes, both will have the same period, natural period. And this being more flexible, this will oscillate more, so therefore it will kind of take away the energy from the main structure. This is what the principle of dynamic vibration absorber. They are appendages to building adding M, C and K. Okay, whereas those were the special structural element. They were not such as appendages. They will be putting into braces or something, some other places where they will take part in the flow of forces, where they are actually taking away the input energy being tuned. That's called tuned. Why they are tuned? Because the fundamental natural frequency of the main structure or the appendage structure are very close. So when the structure shakes, the maximum energy, this being a flexible system, because period is a ratio of M upon K, maximum energy will be dissipated by this thing. It can be liquid damper, it can be mass damper also. Okay. So let's one of the devices which some of our my successors resource person will be talking about is a base isolation. I have deliberately missed base isolation here. Base isolation is another, you can say, a protective system, but it works on slightly different principle. It works on a slightly different principle in the sense the seismic base isolation is placed at the base of the structure. Okay. And what does it do? It kind of filters the high frequency ground motion. This being a flexible system, what happens that is it's able to stop the high frequency ground motion getting transferred into the main structure. But it will have some damping also. Okay, so it's essentially a not exactly a supplement energy dissipation device, but it's a base isolation device which isolates the base or which kind of stops the high frequency ground motion entering from base to the structure, but it will have some damping also. That is why it is sometimes put into the category of passive control devices. But there is a difference. When your building is in the acceleration sensitive region or your superstructure is quite stiff, then only these base isolation things will work. The difference, whereas in case of supplement energy dissipation, your structure should be in this range. Because there has got to be some relative displacement between floors, then only your supplement energy dissipation device or passive energy dissipation devices will be able to dissipate energy. Typically, you can say supplement energy dissipations are or dynamic vibration absorbers are good candidate for tall structures where wind-induced vibrations are likely to happen. So you can say that your flexible shear type structure, your dampers are the better candidate, whereas your superstructure is very stiff in the period range of, say, you can say 0.5 to 0.9. When your superstructure can move rigidly like a single mass, where your base isolation works well. Whereas your structure is very flexible shear type, your flexible supplement energy dissipation will serve your purpose better. Now let's move on to modeling and analysis of supplemental energy dissipation devices. So these are the viscous dampers where essentially they are velocity dependent and it has got damping coefficient and they are fluid and they are being orificed from one part to the other. When the piston in the cylinder moves, this oil moves from this direction to this direction. So the friction or the viscosity in the oil will help in the dissipation of energy, and the slope of this curve is almost flat. So it will have some difficulty in the sense there is no restoring back. So typically when you have a viscous damping device, restoration is an issue because they do not come back their own. I mean, if the ground motion reverses, then it's a different thing. But at the end of the cycle, they don't come back. So what you require is that you typically place some other restoring devices like springs, or you have then viscoelastic systems are better candidate as far as restoration is concerned. In that case, they are not only velocity dependent, there is an exponent on the velocity. Then there are hysteretic dampers where the metal yielding is the one. This is the friction devices, and this is velocity dependent, velocity exponent dependent, and these are, I'm sorry, this dot is not there. They are displacement dependent. Okay, this is purely displacement dependent. This is displacement as well as velocity. Okay. And this is the curve which tells you that how the damping. You can see that because of the damping, your spectra is getting down. From here it has come down. and because of the damping, your period is also shifting. So your performance point has moved from this place to this place. This is a graphical representation which tells you that what is the impact of damping. Damping will have reduction in demand. It will have reduction in the period of the structure. So therefore your performance point is coming down. There are methods of analysis. There are equivalent static methods given in ASCE 7, ASCE 41 and FEMA also. But what is required in design of systems with supplemental energy dissipation devices, that what you require is all supplemental energy dissipation device are to be prototype tested, and you should be able to know what is the effective damping and what is the effective stiffness of it. If you know these through prototype testing based on standard loading protocols, then only you can use that equivalent static methods. Or else there are good number of mathematical models of supplement energy dissipation device which give the force of it, which is a function of force, displacement as well as velocity, can be linear, can be non-linear. You put them into its response history analysis equation and you can do the time stepping integration. And one thing you must understand that most of the supplemental energy dissipation devices are factory made, custom made, patented devices. So the device manufacturers, there are many, they will give you the force deformation behavior of this thing. Or some of the devices which have become very popular, the literature will also give you the force deformation behavior, which will be used for analysis model. And there are some cautions that we have to see. This is the north side view of our newly built lab. In one of the lectures, I noticed somebody asked, how do you put supplement energy dissipation devices? The answer to this is very simple. See, at the end of the day, there are structural elements. They are special because their energy dissipation is substantial. They are special because their force deformation is very well known to you. They are special because they are manufactured under controlled conditions. But end of the day, they are structural devices. They will add some stiffness, they will add some damping. And the supplement energy dissipation devices will not so much of a mass problem. So wherever you put them, they are going to create a structural irregularity also. Therefore, you just can't put them random and you cannot create structural irregularity. So you need to have some specific understanding of the behavior of the structure, and based on that, by and large, you have to place them symmetrically so that you do not create any structural irregularity. That is the fundamental rule. Another thing that you must understand is that spring to restore, you have to replace after earthquake, and maintenance. These are the three things you must all the time understand while choosing a supplement energy dissipation device. There are some of the pictures which will show you that where the supplemental energy dissipation device have been used recently. This is how it looked like. These pictures have been taken from a paper from Seman et al, which is available to the researchers when they search on the Google and all. This is the viscoelastic damper. These are the buckling restraint braces, which is again a metallic yield. When buckling restraint braces are special devices, but metallic yield devices only. Okay, they have been developed by Nippon Corporation in Japan, and there are umpteen number of papers and books, etc., on buckling restraint braces. I did not, deal with them specifically because there is a special category of devices, and but in terms of classification, they are metal yielding devices. Then they are friction devices. They have been used, and that is all I wanted to share with you. I acknowledge Professor T.K. Datta, Professor Murthy, Sri Mali Saab, and Jaswant Arlekar for helping me and helping me in preparing and sharing my knowledge. And this is a question time, and I am grateful to LD College, Sangvi Saab, Principal Ma'am, and all their volunteers, staff members, and everyone who have given me opportunity to share my experiences on that. So yes, sir.
Sir, Sir,
I thought I
it
must give
was
sufficient time for questioning. So towards the end, I just tried to finish it early so that we get enough time for questioning.
right, sir.
As I can notice, there are substantial number of students in the audience. So let me say if there are there must be some questions obviously.
Right, right, sir. Uh, it was a really, sir, very good session, and I think a lot of questions will come.
Yes, please. I'm ready.
Yeah. Please, participant, please raise your hand and ask questions. The forum is open for discussion, please.
Yes, please. So your campus is operating online or it's operating in the conventional mode? Your college?
Right now it's online mode, sir. Because
Achha, no campus-based classes.
earlier we have started, but now because of the possible third wave, it was not started. But now I think everything is okay. So we supposed to start first week of March or last week of February.
Yes, Amira. Are the
Yes, sir.
participants there or they are gone into sleep mode?
Yes, sir.
Yes, means they
Sir,
are
thank
gone
you
into
very much.
sleep mode.
No, sir. Maybe all are alert. Yes, sir.
Yeah.
Thank you very much, sir. It was a really wonderful and informative session for all of us. Each and every concept was touched in a well-organized way, which helped every participant to enhance their knowledge. You make us clear with various important topics like supplemental energy, dissipation devices, and all methods like demands and capacity in terms of engineering as well, and 3LD.
I deliberately called the term LD, actually keeping LD into mind.
Yes, sir. Yes, sir. Sir,
Please.
now if you allow, can be open for questions.
Yeah, please go ahead.
Yeah, sure. If you have any query regarding this session, you can ask. Please raise your hand if you have any query.
There are 115 persons logged in. I do not know how many of them are actually there.
122.
122, yes. Plus 150, I mean, yes. Mahajan Nitendra Gobind Bhai.
Yes, sir. I just want to.
I would like that anybody raising question, please switch on your camera so that I can, we can talk eye to eye.
Actually, my computer do not have camera, sir. So that's I cannot.
The computer does not have the camera. Okay. Anyway, fine.
Okay, sir,
Chaliye,
I want to just ask that for base isolation, one great example is Bhuj hospital. So, is there any great example for energy dissipation in India?
I mean, how do you call an example a great example? It's the first case. See, first case, which was much publicized. See, you must understand all these devices are basically manufactured items. They are manufactured products. So why Bhuj got so much publicity? Because it was, first thing is that it was post Bhuj earthquake. And the isolation devices were supplied by Robinson Seismic, which itself is a reasonably old company. Okay, so that is why it got publicity. But otherwise also the supplement energy dissipation devices, there are some buildings in Gurgaon, etc., where I would not like to name the company, but some friction dampers have been used. But this, see, typically क्या होता है, जब ये devices लगते हैं तो public building में लगते हैं तो वो accessible होता है सबको. लेकिन अगर प्राइवेट बिल्डिंग में लगता है तो वो पब्लिक के लिए एक्सेसिबल नहीं होता है. But yes, I have seen quite a good examples in Japan, but not in India. Yeah, but I have heard about the friction dampers used in some building in Gurgaon. Like, and it's a hotel or some kind of thing, so it's not so much. There is not so much of publicity.
ओके सर, ओके। आई थिंक सूरत में भी अभी टॉल बिल्डिंग्स अलाउ किया है, सो मे बी इन सूरत केस दिस एनर्जी डिसिपेशन डिवाइसेस मे बी हेल्पफुल इन फ्यूचर।
सी आप देखिए, एनर्जी डिसिपेशन डिवाइस को लेके कोई डोंट ट्रीट लाइक ए जादू की छड़ी, ठीक है। अगर आपका स्ट्रक्चर में एनर्जी डिसिपेट करने का कैपेबिलिटी आपको लगता है कि भाई जब एनर्जी अर्थक्वेक का आएगा तो मुझे अपने मेन स्ट्रक्चरल seismic force assisting system में मुझे डैमेज नहीं चाहिए, बिकॉज आई एम ए software company, I have housed some servers, I have, you know, a hospital where operation theater there is no damage is required, then only you do that. But supplementary energy dissipation device is not a substitute for poor main structure. You can't have a poor structure and then put SEDs in place. आपको परफॉर्मेंस एनहांस करना है इन द सेंस कि आपको डैमेज नहीं चाहिए। All buildings cannot be designed for no damage conditions for, you know, design level earthquake.
बट इन इंडियन कंडीशन सर व्हाट हैपन, जहाँ पे जोन 4 है, जोन 5 है, वहाँ पे टॉल बिल्डिंग्स अलाउड ही नहीं किए हैं। दैट्स व्हाई आई मुझे ऐसा
ये मिसकंसेप्शन है कि टॉल बिल्डिंग्स आर मोर वल्नरेबल टू अर्थक्वेक। आप देखिए, आप ब्रॉडली ये समझिए, व्हेन यू लुक एट द रिस्पांस स्पेक्ट्रा, most earthquakes maximum energy is within the period range of 0.6, 0.7, 0.8 second. Okay, and any building who is 15 story above is beyond that. So tall buildings, well built without any irregularity, are not having any risk. See, our perception of tall well built, well made, well constructed, well designed, good configuration tall building is not vulnerable to earthquake, so much so it is subjected to wind induced vibrations. So supplemental energy dissipation devices including tune mass dampers are used to control wind induced vibration also. ठीक है, जैसा मैंने शुरू में ही कहा था कि to understand application of any structural system or device, you need to understand the dynamic characteristic of the building and dynamic characteristic of the ground motion. और ground motion की dynamic characteristic समझने का best तरीका है, you draw the response spectrum, and in the response spectrum your maximum energy is within 0.7, 0.8 second. Then any building which is 1.5 second, say 15-20 माले, they are much away from the maximum energy. Understand? I hope I am able to make sense.
यस सर। सर लेबोरेटरी में उसका मॉडल बना के टेस्ट करना मींस किसी ने काम किया है क्या इस पे? लेबोरेटरी में टेस्टिंग लेबोरेटरी टेस्टिंग इज पॉसिबल फॉर दिस मींस विस्कस डैम्पर हुआ या दैट इज एल्यूमिनियम है, तो उसको मॉडल करना बहुत डिफिकल्ट होगा?
नहीं, कुछ मॉडल करना कुछ डिफिकल्ट नहीं है, मैं आपको बताता हूँ। जितने भी डिवाइसेस आपको यूज करना होता है उसका आपको बैकबोन कर्व, हिस्टेरेसिस कर्व लगता है, और उस हिस्टेरेसिस कर्व के बेसिस पे आप कंप्यूटर में मॉडल करेंगे तो उसका एक अलजेब्रिक एक्सप्रेशन भी लगता है। अदरवाइज हाउ विल यू मॉडल दैट डिवाइस? तो वो एक्सपेरिमेंटल ही होता है। द ओनली वे यू कैन डेवलप ए मैथमेटिकल मॉडल for the force deformation behavior of a damper is through experimental. So all the devices have to be first tested in the lab so that you have the input load deformation behavior. I mean, ये कहने की जरूरत नहीं, it goes without saying.
Yes sir.
Otherwise you can't analyze a building. Otherwise you cannot analyze a building which is having a damper or a SED.
What Nitendra is saying, sir, that he's talking about the zone 4 and 5. The Kutch is in zone 5. So generally,
right,
the government is not giving permission of high-rise building in that particular district. So that is a misconception. So most of the time during the meeting, we are saying that you can give the permission. There is as a no problem.
And high rise building का permission आप नहीं दे रहे हैं. Wind, if your concern is wind, see high rise building का permission नहीं देने के पीछे और municipal bodies के अपने constraint हो सकते हैं कि they don't want to spoil their landscape, or maybe they do not have competent engineers to check the design. Those are the different issues. But high rise buildings are not something that you should create such a kind of thing that they are more vulnerable to earthquake.
Yeah, absolutely.
They are not. They are not. See, earthquake behavior समझने के लिए earthquake का frequency और building का frequency समझना होगा आपको. The closer they are, the more difficult the case.
Absolutely. Yeah. और सर दूसरा जो देखा है अभी का जो ऑब्जर्वेशन बेस आइसोलेटेड बिल्डिंग, जैसे बहुत कम बिल्डिंग आ रहे हैं जैसे इंडिया में एप्लीकेशन वाइज. अभी आना शुरू हुए हैं. एक बिल्डिंग नोएडा में, मतलब 2 बिल्डिंग नोएडा में बने हैं. यस. और सी अभी हम लोगों ने बेस आइसोलेशन का इंडियन स्टैंडर्ड अभी बन के रिलीज हुआ है. इंसिडेंटली आई वाज देयर इन द कमिटी. राइट सर. तो अभी it has been submitted for Gazette publication. Hopefully another maybe month or 2 it will be released. तो बहुत बार ये भी होता था कि see base isolation, supplement energy dissipation devices, ये सब substitute नहीं है good structural design का. Right. लेकिन good performance के चलते, in order to have a good performance, special buildings where you can't afford damage or you want continue to run in operation, hospital आपको चाहिए, एडमिसिव बिल्डिंग आपको फंक्शनल चाहिए अर्थक्वेक की स्थिति में, वहां इनकी जरूरत. दे आर नॉट समथिंग कि आम आदमी घर बनाने जा रहा है तो 4 डैम्पर उठा के ले आएगा लगा देगा, ऐसा नहीं है. राइट सर.
सर यस सर.
As far as costing is concerned, costing of base isolated building is concerned, the cost of base isolator, like in the Bhuj hospital, it is almost 10% of the total cost of the building. It was the project was 100 crore and the 10 crore was spent for the base isolator. So is it possible to have a local manufacturer of base isolation in the country, so price of the base isolation may come down? Is it possible?
Yes, it is possible. ऐसे कुछ कंपनीज हैं, एक रेसिस्टोफ्लेक्स करके कंपनी है जो बेस आइसोलेशन डिवाइसेस इंडिया में ही बना रही है.
ओके. कौन सी कंपनी?
सी क्वेश्चन. रेसिस्टोफ्लेक्स.
रेजिस्टोफ्लेक्स. ओके.
हाँ. वो काफी टाइम से रेलवेज के लिए, वैगन्स के लिए वाइब्रेशन एब्जॉर्ब बनाते थे. अभी उन्होंने बेस आइसोलेशन बनाना शुरू किया है. बट क्वेश्चन क्या होता है कि सी कॉस्ट इज अ फंक्शन ऑफ वेयर डू यू बाय. Base isolation device, I have seen it being manufactured. I have seen them cut and seen what is there. There is nothing जो उसमें extraordinary कुछ ऐसा कोई platinum और gold लगा हुआ नहीं है. It is just that it has got rubber, it has got steel, nothing else. Right. तो rubber और steel तो कोई सोने के भाव नहीं मिलता है ना. Only thing is that you have to combine the elastomer and steel such that फाइनल डिवाइस में क्वालिटी कंट्रोल बेटर हो, डिजाइन प्रॉपर हो, और जो उसका आपको फोर्स डिफॉर्मेशन बिहेवियर मिले वो स्टडी और फैट लूप आपको मिले. दैट इज द होल गेम. इट इज ऑल अबाउट डिजाइनिंग एंड क्वालिटी कंट्रोल. रॉ मटेरियल इनपुट उसका इट्स नॉट कॉस्टली, एंड सो फार इट हैज बीन ए वर्चुअल मोनोपोली ऑफ मोस्ट वेस्टर्न और न्यूजीलैंड कंपनीज. एंड दूसरा इंपॉर्टेंट चीज है कि देयर वर नो इंडियन स्टैंडर्ड. So since they were following ASCE or European standard, the companies who are making there will come forward because we did not have a loading protocol. Abhi maybe it is out, or maybe it will be out in few weeks time. Once we have Indian standard for everyone, anyone can make. Yep. And you have to comply with the Indian standard. That's all.
Right.
Yes, please.
Thank you. Thank you, sir.
सर मैंने एक ऐसा भी पढ़ा था कि फ्लूइड डैम्पर्स में जैसे अर्थक्वेक के एक्सेलरेशन से फ्लूइड का विस्कोसिटी चेंज होने से डैम्पिंग में चेंज ला सकते हैं. तो इज इट पॉसिबल सर? कुछ स्मार्ट डैम्पर्स करके कुछ था वो.
हाँ देखिए, स्मार्ट डैम्पर कहो, सेमी एक्टिव डैम्पर कहो, एडेप्टिव डैम्पर कहो, उसमें क्या होता है कि there is a viscous fluid. Viscous fluid में कुछ आयरन पार्टिकल्स वो फ्लोट करके रखते हैं, and then when you apply some current, the iron particle gets aligned, so it gets stiff, तो उसकी stiffness बढ़ जाती है, और it may so happen that जो orifice है उसका साइज कम ज्यादा हो सकता है. So they call smart damper, semi-active damper. ये सब मटेरियल की टेक्नोलॉजी है. You understand that?
Yes, sir,
There
yes.
are various ways when you can control the stiffness and damping of a device, depending upon how do you control that. Yes, please. I can see one hand. If they have already, the question have already been addressed, you can lower your hand.
Yeah,
I think that's all.
Yeah. Yes, sir.
Yes, Amira.
Yes, sir. Yes, sir. Now I guess no one has query. Thank you, sir, for answering all the questions. Sir, I would like to request you, can you please share your presentation with us? Because it
Sure,
will be helpful for all the participants for their reference.
Yeah, I'll send it to Sangvi sir.
Okay, it's great, sir. Thank you.
Okay.
Thank you very much, sir, for such a great session.
Thank you, sir, for accepting our invitation. And I think
it's my pleasure. Come down to Jaipur sometime.
No, sure, sir, we'll come. And I think this is the first of the interaction, and we keep on interacting.
Yes, sure.
Yes, sir. Sir, actually, next month, most probably we are planning to have another program on confined machinery under the GYAN, Global Initiative for Academic Network, and Dr. Svetlana Brezev, she's a.
Svetlana, I know.
Yeah, so Svetlana is going to take the course, and